Hello everyone, I'm Tianyue Zheng from Tsinghua University. My supervisor is Professor Linglong Dai. It's my pleasure to present my research project about large language model-enabled multitask physical layer network here. We are now living in the era of large models. LLMs, represented by GPT, have ushered in a new epoch in the field of AI. Recently, the LLMs have been applied to multiple tasks for a typical transceiver in physical layer communications, including memo precoding, channel prediction, and decoding. So you may ask why we use LLMs for physical layer communications. Recent studies suggest that the LLM-based methods have demonstrated superior performance, especially in challenging scenarios, and exhibit stronger generalization and few-shot learning capabilities. However, most existing methods design separate LLMs for individual tasks. Consider that tens or even hundreds of models are required for different task parameters. For example, different code reads for channel decoding. It results in high training complexity along with substantial storage and deployment overhead. Therefore, my research project is trying to answer, can we unify multiple physical layer tasks with a single LLM? This approach would allow us to retain the advantages of LLM over smaller models while effectively reducing the cost for designing and training multiple separate LLMs. Fortunately, while the LLMs present challenges in deployment and training costs, their capabilities also create opportunities for a unified multitask architecture. Therefore, we designed the multitask physical layer LLM as depicted here. To achieve this goal, we designed three key components to address the critical challenges of this framework. Next, we will illustrate each design briefly. First, to achieve a unified multitask architecture, the LLM must correctly distinguish and understand the requirements of different tasks. To this end, we design a multitask instruction module, which inputs task requirements in natural language to the LLM as prompts. This effectively informs the LLM on which task to perform. The second key issue is to adapt the text-based LLM to different communication tasks. For this goal, we have designed lightweight encoders and decoders for each individual task. Finally, to achieve efficient fine-tuning of the LLMs, we adopt low-rank adaptation, that is, LoRa technique. Specifically, instead of fine-tuning the original high-dimensional pre-trained weight matrix W, we introduces two low-dimensional trainable matrices A and B. Simulation experiments have validated that the proposed method effectively obtains a multitask LLM for physical layer network. In summary, we have established a multitask paradigm where a single LLM can handle multiple tasks. Currently, I'm exploring cross-model joint optimization, aiming to have one LLM power the entire neural receiver. Here are the relevant publications of my research project. That's all for my report. Thanks for your listening.